Hello everyone, welcome to our talk. I'm Gonçalo and I'm here to present 1x1 convolutions by random ternary matrices. This is joint work with Matthijs and Alex from NVIDIA. During this talk, we'll be discussing sparsity and quantization techniques, which are the motivation for using our random ternary matrices. Then we'll discuss some recent convolutional speech models, which were proposed by NVIDIA and are available at NVIDIA Nemo. And finally, we'll discuss some of our results, which improve the Pareto frontiers of several models on several tasks. So let's first take a look at sparsity and quantization. Sparsity enables faster neural networks on existing hardware. For example, NVIDIA Ampere allows for fine-grained structural sparsity to speed up neural networks. Biologically speaking, sparsity is also motivated by our brain, since we know that the brain is not fully connected. On the other hand, quantization reduces the neural network complexity. This is especially important on edge devices, which have bandwidth constraints, energy constraints, and area constraints. In practice, this makes it hard to export to clients, fetch on edge devices, and also store information on chip. Our goal is to make compact speech recognition models even more compact. This is a relevant use case, since speech recognition tasks often have a low latency requirement. Hence, we propose to leverage recent depthwise separable convolutional designs to deepen residual networks efficiently. Let's first take a look at trained ternary quantization, or TTQ, which is a popular method proposed in 2016 to ternarize neural networks. Looking at the figure, we start with our full precision weights, and then we normalize them and apply a threshold t to induce sparsity in the set. So values higher than t are set to a positive value. Negative values smaller than minus t are set another negative value, and values in between are set to 0. The positive and negative values are referred to as scales, and these scales are learned during training. Hence, we ternarize the floating point weights by applying this threshold t, and then we train by backpropagating gradient 1 to the floating point weights and gradient 2 to the scaling factors, which are referred to as Wn and Wp in the figure. When we apply TTQ to train our networks, we realized that after training, the ternary matrices did not have any obvious structure and resembled random ternary matrices. So here we have two matrices, one of which is random and the other one was trained by TTQ. Can you tell the difference between them? On the left, we have our trained ternary matrix, and on the right we have a random ternary matrix. So in our opinion, they look quite similar, and we use this as the motivation of our approach. Here is an example implementation using PyTorch of our random ternary quantization approach. We simply assign fixed random ternary weights to the network and do not update them during training. First, we simply initialize the weights as usual, for example using a uniform distribution around 0, such as the K-mean uniform. Then we compute the signs by getting a one-hot encoding of the indices that are greater than 0 and smaller than 0. To induce weight sparsity, we simply compute a mask. This mask consists of the indices which have absolute values higher than the threshold t, similarly to TTQ. The next step is to make our weights ternary. Since we do not have a positive or negative scale, we simply subtract a one-hot encoding of the positive indices with the negative indices. Then we simply multiply those by the mask. Finally, since we do not wish to update the ternary weights during training, we simply set PyTorch's requires grad parameter to false. Please note that this is just an example implementation. Our algorithm allows for a wide range of implementations that may benefit certain hardware or software designs. In our algorithm, We only create random ternary matrices once before training. The ternary assignments, -1, 0, and +1, remain constant throughout training. Moreover, scaling factors are learned by preceding and subsequent layers, so we do not learn them ourselves. In our case, sparsity is controlled by a constant threshold t, but any other ternarization scheme would work. Effectively, in our approach, each NIR only computes a difference of activation sums, which may be scaled by a batch norm layer, which is then passed through a nonlinearity such as ReLU. This is also presented in the expression below, where I+ and I- represent the sets of all indices of the connections with the weights +1 and -1, respectively. Please note that the union of these two sets may be sparse, meaning it may not contain the indices of all connections, namely the connections with weight 0. This process is further illustrated in the figure on the right. Using random ternary matrices has several benefits. First, it allows for faster training, since no weights need to be learned or updated. Also, it allows for faster on-chip inference, since no multiplications are required and sparse operations are in play. Finally, we can achieve higher compression rates, since no weights need to be stored. They can simply be generated on the fly. Our simplified speech models consist in modifying the residual blocks of QuartzNet and MatchboxNet. In this example, we see the weight matrices of a trained MatchboxNet with 3 blocks, 1 subblock, and 64 channels. One of our modifications is to use identity skip links. In this version, we change the quadratic skip links to identity weight matrices during training. As previously discussed, we propose to use random ternary weights for the 1x1 convolutions in the residual path. Depending on the threshold t that was used to form these random ternary weights, we can achieve high degrees of sparsity in these 1x1 convolutions. Our simplified speech models offer a dramatic reduction of the weights to be trained. This allows us to increase depth, meaning the number of blocks or subblocks, efficiently. Now let's take a look at some of our results. We start by evaluating automatic speech recognition with QuartzNet on AN4. AN4 is an alphanumeric database of around 1,000 utterances averaging 3 seconds long. They consist of personal information such as birthdays, addresses, and phone numbers. Even though AN4 is a small dataset, it helps us iterate fast in these experiments. Here, we evaluated several configurations of QuartzNet. Namely, we have 3 or 6 blocks, 1 or 2 subblocks, and 256 or 512 number of channels. Hence, we are experimenting with deeper and wider QuartzNets. Looking at the previous Pareto frontier of these baselines, we observed that deeper QuartzNets achieve a better trade-off in terms of word error rate and number of parameters. We compared our simplified variants against these baselines. Namely, we use random ternary matrices for the 1x1 convolutions inside the residual blocks. On top of that, we use identity skip links, both with random ternary 1x1 convolutions and floating point 1x1 convolutions. We observed that our simplified variants improve the Pareto frontier of the baselines, establishing a better trade-off between performance and number of parameters. We further tested how sparse could we go using trained skip links. We use the same variants as the ones described before for QuartzNet. Varying t from 0 to 1.0, where 0 means a binary random matrix and 1.0 means a zero-valued matrix, we see that we can get away with a very high t-value, which would allow us to go extremely sparse in these random matrices. We also note that bigger variants of QuartzNet are less sensitive to different t-values. If you'd like to train your own QuartzNet on AN4, please check NVIDIA NeMo's tutorial on automatic speech recognition with NeMo. We also evaluated speech command recognition using MatchboxNet on Google Speech Commands. Google Speech commands consist of 1 second spoken utterances of several speakers. Version 1 only has 30 commands. These commands were chosen for possible IoT application scenarios as well as numerical digits. Similarly to QuartzNet, we also analyze the improvement of the Pareto frontier here. We use several MatchboxNet baselines. For example, we use 3 and 6 blocks, 1 and 2 number of subblocks, and 64 and 128 channels. We also observe here that deeper models achieve a better trade-off in terms of error rate and number of parameters. Overall, we also see that our simplified variants improve the Pareto frontier on MatchboxNet. Once again, if you'd like to train your own MatchboxNet on Google Speech commands, please check NVIDIA NeMo's tutorial on speech command recognition with NeMo. We also evaluated large-scale speech recognition on Librispeech. Librispeech contains around 10,000 hours of segmented and aligned narrations of public audiobooks. For our floating point baseline, we used QuartzNet with 15 blocks and 5 subblocks. As originally proposed, the number of channels varies within each block. In the table, we can see that our baseline achieves 3.98% word error rate on DevClean and 3.83% word error rate on TestClean. Moreover, we can observe that it has around 90 million floating point parameters. For our simplified variant, we would like to note that QuartzNet's letter blocks contain most of the parameters. Hence, we propose to ternarize blocks 10 to 15, which reduces the number of trainable floating point weights to half. Even with around 50% of the parameters being now sparse random ternary, we only sacrifice around 1% word error rate on TestClean and DevClean. More specifically, we can see in the table that our random ternary variant achieves 4.84% word error rate on DevClean and 4.93% word error rate on TestClean. However, only around 9 million weights are floating point and learned, whereas the other 9 million weights are random ternary and do not need to be updated. As we are reaching the end of this talk on 1x1 convolutions by random ternary matrices, let's provide a brief summary. We have seen that using random ternary weights provides several benefits. Specifically, it allows for each neuron to only compute a sparse sum of its inputs. Therefore, no floating point matrix multiplications are required. Due to the random nature of these ternary weights, they can be generated on the fly and do not require any memory accesses. Finally, we have seen that using random ternary weights improves the model Pareto frontiers on several models and tasks. Therefore, our simplified models achieve a better trade-off between model size and performance. Our approach is also widely applicable to current neural network architectures. We propose to use random ternary weights on the 1x1 convolutions or fully connected layers, which are commonly used in practice. Specifically, with the increased popularity of residual networks, our approach allows us to have deeper networks at a reduced cost. Since residual networks are widely used across different data domains, we hope that our approach might be beneficial on different application scenarios. Our method is energy efficient and suited for existing hardware, allowing for a range of possible implementations. For example, the sparse sums of the activations may be simply realized by wiring. Moreover, the difference of sums may be performed by using an operational amplifier. Hence, at inference time, our algorithm may be mapped to analog hardware. Note that the sources of noise are reduced, since the number of required digital to analog converters is linear in the number of activations. Please feel free to check out NVIDIA NeMo's tutorials at GitHub. For our experiments, we adopted the training settings publicly available there. So if you wish to replicate our results or apply our method on additional speech tasks or models, feel free to try it. We thank you for being interested in our talk, and hopefully you'll consider using random ternary matrices in the future to further compact existing network designs.